just want to welcome Anna Goldie, who's here from both Google Brain and Stanford. Thank you.
Thank you so much. And I feel lucky to have been preceded by that talk on graph neural nets and generalization. It's actually a very relevant setup for this talk. I think we have some similar findings. So today I'm going to talk about model parallelism and chip floor planning with deep reinforcement learning. And I just wanted to start off with some brief motivation. Basically, we co-founded this team, Azalia, Mir Hosseini, and I, like 3.5 years ago, with the kind of intuition that in the past decade or so, systems and hardware had transformed machine learning into something that was very effective at certain types of combinatorial optimization problems. And we believed that it was time for machine learning to return the favor and transform the way in which we design these systems and hardware and kind of close the loop here. And some of the further motivation that we had was just this data, say, coming from OpenAI, showing that the amount of compute usage was doubling roughly every 3.4 months in the largest AI training runs, whereas Moore's law, before it had basically ceased to hold, was compute usage, or sorry, compute resources doubling every 2 years or so. And so we kind of need to do something to close this exponentially growing gap between supply and demand. And I think further with that more recent scaling law work, it kind of matched our intuition that compute, like hardware and systems, are kind of the fuel for progress in AI. And we also had this observation that a lot of problems in systems are just combinatorial optimizations on graph data. So for example, compiler optimization, chip placement, data center resource allocation. For compiler optimization, you take as input an XLA or HLO or high-level operation graph. The objective is just to schedule or fuse operations. And in chip placement, you take in a net list, which is a graph of chip components, and you want to place them onto 2D or maybe effectively 3D grids. And then say data center resource allocation, very similar. You take in a graph of job workloads, and you want to place them into data center cells and racks. So really, these problems kind of have this similar underlying structure. And we saw certain advantages to taking a learning-based approach. And so unlike traditional approaches like branch and bound or hill climbing or ILP solvers, ML models can actually learn the underlying relationship between the context and the target optimization metrics, and leverage that to explore various trade-offs in the optimization space. So it's a more white box method. And these models can actually gain experience as they solve more instances of the problem, and they can become basically experts over time. They can potentially solve far more instances of a given problem than any human would ever experience in their lifetime. And also, you can scale these models on distributed platforms. You can scale them arbitrarily to have an arbitrarily large number of parameters. So in this talk, I want to go over 2 case studies of combinatorial optimization problems in system design, and machine learning approaches that we took to solve them or to generate more effective solutions to these problems. The first I'm going to talk about is device placement, or model parallelism. And so what is that, and why should we care about it? So the trend in machine learning models is that they are becoming larger and larger, and state-of-the-art models can have billions or even trillions of parameters. Even this slide is kind of out of date at this point, and the largest models are even much larger than that. And so the memory capacity in modern hardware is not scaling at the same rate. So really, if we want to be able to train the highest performing models, we potentially need to be able to partition these models across multiple hardware devices. But the way in which you cut or partition that graph can have significant implications for the time it takes to train or infer that model. And it's an interesting problem in its own right. So in this work, we pose device placement as a reinforcement learning problem. So we take as input a neural network graph of operations and a set of available devices like CPU cores, GPU cores. You could potentially map them onto other types of hardware devices like TPUs. And we have a RL model, a policy, that outputs an assignment of the operations in these models onto the set of devices that are available. And then we can actually run this on real hardware, use the runtime as a reward signal to provide feedback to the policy and allow it to become more and more effective at the task of assigning these ops on devices. So this model that we had at first was this sort of end-to-end hierarchical placement model. And you can tell this is a bit older because it doesn't actually use graph neural networks, but we're going to get to that soon. So we basically have this embedding, which contains information about the types of the operations, the shapes of the outputs, and the adjacency, the connectivity between the ops. And we have basically one model that first groups the operations into clusters of ops, and then we place groups, because this would allow us to scale to the largest ML models that we were seeing at the time, whereas placing all of them at once was not computationally feasible at the time. And we use the seek-to-seek model to place the operations, the groups of operations one at a time onto CPU and GPU cores. And so this for fun, here's a learned placement on a neural machine translation model. Kind of looks like some Christmas tree lights here. So the top is a decoder model, various like layers, softmax, attention layers 1 and 2, and embeddings, and an encoder. So it looks kind of random. You can notice that the embedding layers were all put on CPU, which makes sense because there's more memory capacity there. But it's kind of hard to understand, like, why would the RL agent choose this particular arrangement of groups onto devices? And so we did some profiling for this particular model. So on the left is the RL-based placements, sort of operation runtime per GPU core. So it's kind of a measure of the load balancing performance of the model's assignment of ops onto devices. So you can kind of see that compared to the placement on the right, which is generated by a human expert, the RL placement was much more load balanced, which I think, which explains potentially why it got better results. Whereas the human expert, maybe they were looking more at the forward pass, and so they actually ended up not taking fully into account the time spent in the backwards pass, which resulted in them not actually successfully load balancing the ops in their device placement assignment. But then we also looked into, say, an Inception v3 model. And in this case, you know, so by the way, each of these colors is a different GPU core. So this case is these branches are parallelized onto different GPU cores. That kind of makes sense. But there are also some random artifacts. It's not totally clear why would the RL agent choose to, say, assign to this core and then to that core. So we also looked into profiling for this particular model. So when we looked at the load balancing kind of angle from the previous NMT model, we can actually see that the RL placement was not as load balanced as the human placement on the right, because the human placement was actually a data parallel approach, where you just take 4 copies of the model, divide the training data into 4 pieces. And so it's pretty hard to compete with that in terms of a load balancing objective. But if you look at the time spent on mem copies, basically the communication cost between devices, the data parallel approach on the right actually has to spend significant time copying the gradients to the parameter server at the end, whereas this model parallel approach developed by the RL agent is actually spending far less time on communication costs. And so overall, the trade-off there works out better for the RL placement. But you know, for this previous approach, we were looking at just training a model from scratch for each new graph that we encountered. And really, that's just not as useful if, you know, you're a machine learning practitioner or researcher. You don't want to wait for, you know, 6 hours for this RL policy to converge and give you a placement. You want to be able to pre-train some policy and then quickly generate a new placement of the ops onto devices. So we were doing some follow-up work with colleagues like Yanqi and others, and we were working on basically generalized policies for device placement, with the objective here being we want to minimize the expected runtime over a set of graphs here. So the reward here is expected runtime. And here we use graph neural networks to generate representations of the graph, and we use an Transformer XL based laser network to do the placement. And this work was led by Yanqi Zhou and these other co-authors. And actually, it was able to achieve much better generalization results than that previous model with the fixed handcrafted embeddings, which makes a lot of sense to us. So here are some results on various RNN-LMs, GNMT, Transformer XL, and some vision models as well. So here, if you're interested, there are some other papers that we had on basically device placement or model parallelism with RL. And the last one was actually presented at NeurIPS, so I should have updated that slide. It's not just on arXiv anymore. Now I'm excited to talk about some more recent work that we did on basically reinforcement learning for chip floor planning, which is another combinatorial optimization task. And I just want to thank all of my collaborators in Google Brain and the TPU team. So this is a collaboration with physical design engineers who are building the TPU. And we recently published this work in Nature. Please check out the article if you're interested. And yeah, this generated some media attention, and we're excited to continue to make progress in this area and to see what other people do in the future. So first, I just want to share some of our design goals when we were starting this project. So basically, chip design today, it takes years. I think 1.5 to 2 years is actually an underestimate, more like 2 or 3 years to design a new, a major new chip. And that's a big problem because the pace at which machine learning advances is far faster. And so we actually have to when we're designing a new chip, we have to predict which neural net architectures are going to be prevalent in 2 to 5 years in order for that chip to actually be useful. And really, there's a lot more performance that we could achieve if we could co-evolve neural nets and hardware. And actually, we have some work on that where we show that if you could, change the data path and schedule for a TPU-like hardware, you could achieve significantly higher performance, like 8.5x. So really, there's just a lot that's being left on the table, and just generally the observation that the neural net architectures that are winning today are kind of the ones that have won the hardware lottery, and that's a bit arbitrary. Like maybe there are other architectures that are actually more effective that just aren't feasible on today's hardware. And just generally, we would like to enable cheaper, faster, and more environmentally friendly chips, and kind of democratize the process of chip design so that more players could actually design custom hardware for their own tasks. So first, I'm going to introduce to you what is the problem that we tackled in this work and our approach to that and how we achieve generalization. So chip planning is just a form of graph resource optimization. And so the objective is that you take in a graph of chip components, which is called a netlist, and it contains memory components, which are called macros, and standard cells, which are logic gates like NAND and NORs, all connected by wires, so it's a graph. And the objective is to place it onto a 2D, or maybe it's more like a 3D canvas, such that you minimize various costs, like latency of computation, power consumption, area, while adhering to hard constraints. And this is a very complex problem. The previous towering challenges in AI that have been addressed as reinforcement learning, like chess or Go, have only 10 to the 360 possible states, whereas a simplified version of the chip placement problem has 10 to the 9,000. And there's been decades of research, five or six decades of prior research on this problem, with prior approaches falling into 3 broad categories: partitioning-based methods like min-cut, stochastic or hill climbing-based approaches like simulated annealing, and analytic solvers like the prior state-of-the-art replace. And in this work, we propose a 4th category of approach, learning-based methods. And more specifically, we pose chip floor planning as a reinforcement learning problem. So where we place the nodes of this chip netlist graph one at a time onto the canvas, and at the end, we can measure the quality approximately of this placement and use that to update the parameters of our policy and get better and better at this placement task over time. So to make this a bit clearer, I'm going to share with you the kind of Markov decision process for this problem. So the way we modeled it was that state at each time step is an embedding, a representation of the chip netlist that we're placing, a representation of the current node, and a representation of the canvas that we're placing it onto, and maybe which regions have already been filled by components. And the action at each time step is basically a decision of where do we place the current node onto this 2D canvas and which grid cell. And the reward is, after placing all the nodes, we take the weighted average of wire length, so the sum of the wires connecting all the components, density, and routing congestion, which is a measure of the extent to which we've exhausted the routing, the connectivity resources between these nodes. And so here, for fun, here are some results on a TPv4 block. And unfortunately, I have to blur this due to confidentiality. But the white regions are macros, so these memory components I was describing. And then the green cloud is logic gates, standard cells. So as you can see, our placement on the right, the RL placement generates this kind of smoother, more rounded placement that actually reduces wire length, which is one of the key metrics. And notably, the human expert placement on the left actually took 6 to 8 weeks to generate, and it's not as high of a quality, whereas the placement on the right took only 24 hours. And this result is from about 2 years ago. So actually, we've significantly improved the speed of our methods, and I'll explain a bit more how we did that in the rest of the talk. So just to be a bit more concrete.
So Anna, I have a question in Q&A. Do you want me to
sure.
generally interrupt you with questions, or do you want to take them at the end?
Yeah, sure. That's more interactive. Sure, let's do that.
So Linda asked,
what was the question?
Can the RL model adjust to changing number of devices? For example, a device joins or leaves during iterations of training.
So we're talking about device placement.
Yeah, sorry, it was a couple minutes old.
Oh yeah, sorry, I can't see the questions while I'm talking. Okay. So you're asking if, I think maybe for the generalized policy, we could, we don't need to retrain when we get a new instance of the problem. So that actually should be fine. Like the first version of this work, it wouldn't be robust to that. You would need to retrain if you change the number of devices. But if you actually have a policy that generalizes, you could give it a different set of different number of devices to place onto, and it would be fine. Good question. And that shows why generalization matters. Did that answer the question?
She said, okay. Thank you. So I think so.
All right, great. I hope so. So here, again, I have an objective function, which is basically given parameters of the policy and the set of graphs of chip netlist graphs that we're looking at in our training data. The goal is to maximize the expected reward. So this might look pretty familiar from the device placement example. It's very similar. But in this case, the reward is a bit different. It's the negative weighted sum of wire length congestion and density as described earlier. So in this work, we took a hybrid approach to placement, chip floor planning optimization. And we used the RL agent to place the macros one at a time onto the canvas. And then we used a force-directed method to place the standard cells. And it could do so quite quickly. I think standard cell placement was considered almost a solved problem. So we could kind of leverage that to very quickly place standard cells and just use that as part of the inner loop for RL. But now I want to talk about how we achieve generalization for this chip floor planning problem. And so in the like device placement, the first iteration of this work, we had a policy that we would train from scratch for each new chip netlist graph that we wanted to place. And it would take tens of thousands of iterations to get kind of good at the task of placing this particular chip, which is sort of generally less exciting, but also from a practical perspective, if we want to be helpful to chip designers, it's not very acceptable that they should wait 24 hours to get a placement. Maybe we can be much faster. So we wanted to move toward this regime where we would pre-train a policy on a variety of different chip netlist graphs and then kind of fine tune it or even just generate zero-shot policies in seconds for a new previously unseen chip. But the question is, how do we achieve that? So the first attempt that we made to get our policy to generalize were the obvious. We tried just using our previous RL policy architecture, trained on multiple chips, and just testing on a new previously unseen chip. And we got very poor results with that. we tried various other schemes like freezing different layers of the RL policy and then testing it on new unseen chips. That also didn't work. So the question is, what did work? Basically leveraging supervised learning to find the right architecture. But we actually didn't use the pre-trained weight, so we just used it to find the architecture, but I'll explain what I mean. So basically the observation was that the reason that our policy was doing so poorly at generating high quality placements for a previously unseen chip block was because the value net was failing to predict the quality of placements for that block generated by the policy. And so we decided to basically decompose the problem. Predicting the reward is pretty related to the task of, predicting the value net output for a given placement. So we thought maybe this is strictly an easier problem to generate, to train a model that can predict the reward. And in order to solve the larger problem of how to generate high quality placements, we kind of need to solve this subproblem anyway. So we decided that we wanted to try to train policies that were able to accurately predict reward from off-policy data from a variety of different chip blocks and qualities of placement. So in order to achieve that, we compiled a data set of chip placements using our previous RL policy. So basically, we can generate effectively infinite labeled data by using our old RL architecture to generate placements for different chip blocks, and then kind of capturing placements throughout the course of training. So we would have a variety of different qualities of placement, and then labeling them using the same reward functions that we provide as feedback for our RL agent. So here you can see on the right, wire length and congestion costs for a variety of different net lists. Each color represents a different chip net list. And so this kind of creates this playground where we can explore different neural architectural choices to find one that would actually be good at encoding the input problem. So here's a setup that we used here. So we had what we were varying here is this graph convolutional neural network, this first white box. And so what we feed as input to that to that model is the features of the nodes that we're placing, so their XY coordinates, or that we've already placed. So we're basically feeding it a placement and it's predicting the reward. So for each of the nodes that have been placed, their XY coordinates, their width and height, and the type, what function they play in the chip, as well as information about the overall graph, like the number of macro standard cells and clustering of these components. And we also feed metadata about the overall chip. And then we feed this into a pretty thin, fully connected model that predicts wire length and congestion. So really this graph convolutional neural network is doing the heavy lifting here. And so we tried a variety of different architectures for this component, and the one that produced for us the best results was this edge-based graph convolutional neural network that I'm going to describe a bit next, but it kind of makes sense intuitively. So a lot of problems or graph neural network approaches kind of focus on the features of the nodes, and for some problems like say social networking, things like that, it makes a lot of sense. But for this problem, it's really all about the edges. So what is the longest path in this in this graph that we've placed? What is the total wire length? So it kind of makes sense that a representation that focused on edges would be helpful here. So the algorithm that we landed on was we feed these features of the nodes into a fully connected network to generate an initial representation for all for each node. We then generate a representation for each edge by concatenating these the representation for each node that it connects, and then we pass that into another fully connected network, and then we get a new representation for each node by taking the mean of the representation for each edge it participates in, and then we just rinse and repeat. We found that in practice 7 times worked well for our problems, meaning that in practice each node is affected by the nodes within its 7-hop neighborhood. And then at the end, if you want a representation for the entire graph, you can just take the mean of all the edges. So if we look at the results for how well can this architecture predict the quality of placement, for wire length, it's quite effective. The correlation here is very strong. For congestion, it's a bit noisier, but congestion is a noisier metric overall. And there's still clearly a correlation here. And in practice, it was strong enough that using this model was actually helpful for us. So here, I'll show you how it fit into our overall policy value model architecture for the RL agent that we use to place these chip net lists. So here on the very far left, this graph convolutional component was basically serving as the encoder for our policy and value networks. So the policy network is a deconvolutional neural network that generates a probability distribution for the current node over each of the grid cells on this chip canvas. And then the value net here generates a kind of a prediction of the quality of the placement so far. And you can kind of imagine how it would be doing better now that we have this more effective encoder for the input graph. And here, I wanted to show you a placement of an open source RISC-V Ariane CPU core. On the left is a policy that's trained from scratch. So each of these squares is a macro. The policy is, on the left is a policy that's being trained from scratch, so it's never seen a chip before. And on the right is a policy that's been pre-trained on a number of chips and is now being fine-tuned on the same previously unseen chip. And so as you can see, the policy that's fine-tuned, it already kind of starts off with something close to what it will end up converging to. So it leaves this convex hole in the center for the standard cells to be placed. And that actually helps to minimize the wire length connecting the macros to these logic components. And on the left, the policy trained from scratch eventually converges to something similar to the policy on the right, but it actually is slightly lower quality. So this kind of shows that you can actually get better performance and faster in certain cases by pre-training. Yeah, and here you can see the convergence curves for these two models. So the blue line is a model trained from scratch, and the green line is a fine-tuned policy. It actually takes almost 40 hours in this case for the model trained from scratch to kind of approach the pre-trained model performance on the placement cost. So here is some other generalization results. So here you can see that as you pre-train for a larger number, if you take a zero-shot model, which is basically generating a placement in a sub-second, it's actually like not so much. And then as you fine-tune more, you get better results. But the model that was fine-tuned for 12 hours still does better than the model that was trained from scratch, but fine-tuned on this block for 24 hours. I think what's exciting most to me though is this final graph here, which is basically we're showing the effect of the training data set size on the convergence properties. So in this domain, 20 blocks is actually considered a relatively large data set, which is kind of silly. As you go from just 2 to 5 to 20 blocks, the zero-shot performance here, which means that we've done zero fine-tuning on this block, is actually significantly improving. And then, as we go to the left, to the right on this x-axis, is different amounts of fine-tuning. So it's kind of encouraging. It suggests that if we could get access to more chip blocks, either by companies sharing data or through data augmentation, we could potentially push the performance of the zero-shot model to be closer and closer to that of models that have been fine-tuned for many hours. And what's exciting about that is because it has implications for basically co-optimizations with other stages of chip design. So chip floor planning is kind of towards a later stage, like right before you might tape out a chip. There's a few more downstream, like detailed routing optimizations, but there are a lot of decisions that are made quite early on that have impact on the performance, the basically power consumption and other properties of the final chip that really would benefit from faster feedback. Like if it takes humans like months to generate a high quality placement for a given graph, it's really hard to experiment with different compositions of that graph. So we're very excited to kind of push towards high quality zero shot or few shot RL policies. And so here, finally, I wanted to show some results against the previous state-of-the-art baseline. So replace was that state-of-the-art, prior state-of-the-art, analytics solver, and manual was kind of the real state of the art, which was human experts spending months to place these are like physical design experts placing them manually. And so here, these are the metrics generated by a commercial EDA tool. This is a very high quality simulation. It can take up to 72 hours to generate these types of results. But these are the metrics that chip designers actually use when they're deciding which placements to send for manufacturing. So these are just timing is related to delays in computation areas, the total area of the chip, power is obviously the power consumption, and wire length is the connectivity, the total length of the wires connecting all the components given the placement, and then congestion is related to whether or not you've consumed all the routing resources on the chip. So as you can see, our method compares quite favorably to these prior approaches. And actually, we were used in the latest TPU. So actually, in January, our Google taped out TPU v5 inference version using placements generated by our method, which is really exciting for us. And we're excited to see deep reinforcement learning have more and more real world impact. If you're interested and you'd like to learn more, here's like a non-paywall link to the Nature article. We also have a Google AI blog post where we explain some of our method. And we also have a number of other papers on combinatorial optimization with machine learning. So please feel free to check them out. And thanks so much for listening to the talk. Happy to answer questions.
Thanks so much, Anna. Do we have any questions from the audience? Well, yeah, I'll ask a question, which is,
Sure.
really large scale optimization problems. It's surprising to hear that there would be any manual component at all in solving them. Why do you think it is that, before your work, there was a manual component? Like, what were people able to do that other optimizers couldn't?
I mean, I think basically this is the first method in 50, 60 years that can actually outperform humans. And it's very important, like you cannot build a chip if you don't meet all of these constraints. And so like there's something like 8 metrics that they care about. You have to be satisfactory on all of them. And they're not willing to compromise at all. So they would rather spend months having humans do this than yeah. I mean, there are other steps of the chip design process, of course, have been automated. This is like kind of this holdout. So that's why we were excited about being able to generate placements that are actually superhuman.
Any other questions?
Are you raising your hand?
Oh yes, Piotr, I see 2 hands raised.
Okay, yeah, I'm raising my hand. But actually, maybe Stephanie, go ahead first.
Well, you were first, so.
Okay. Yes, I was wondering. So the problem of device placement, like on a very surface, it seems potentially related to scheduling issues. So I was wondering if your ideas could help improve scheduling algorithms, right? Like there is a group working at MIT by Mohammed Alizadeh who's working on scheduling. So I was wondering if like some of your ideas could be used there as well.
So we have another paper that I didn't include in this talk that it's under review at ICCV, and we're doing co-optimization of scheduling data path and fusion, and we're seeing very promising results. In that paper, we're not really focused on using RL for it, so we actually think we can get even better results. I think we're using an ILP based method for the scheduling part. So yeah. I mean, we think it's very promising.
I see. Oh, cool. Thank you.
Yeah, no problem. Stephanie.
Okay, thank you. So I had a question about the generalization performance of these models. So you already showed quite impressive results just with pre-training, which kind of indicates that they're generalizing fairly well. But I was wondering if you had looked at like more detailed insights in like on what kinds of instances or axes these models typically generalize well, and on what kinds of axes they may still have difficulties, and maybe you have some insights why.
I actually think that's like a really interesting question, and like we're excited to do more exploration on that. I agree, these are important questions.
Okay, thank you.
Any final question from the audience? If not, then let's thank Anna again. Okay, thanks, Anna.
Thanks so much. This was fun.